Hello again, class. This is Eric Payton, and this is Introduction to Materials Engineering, Chapter 4. So previously in Chapter 3, we discussed crystal structures. We had metallic structures, face-centered cubic, body-centered cubic, hexagonal closed pack structures, as well as atomic packing factor and coordination number. We looked at both amorphous, poly, and single crystal materials, and how the properties of the material changed with these different attributes. We also looked at point coordinates, directions, and planes. So now we're moving on to Chapter 4. And Chapter 4 is Chapter 4 is Imperfections in Solids. Issues to address here are: what is the solidification mechanism? What types of defects arise in solids? Can the type of defects be varied and controlled? How do defects affect material properties? And finally, are defects undesirable? Imperfections in solids. Solidification is the result of a casting of some sort of molten material and the cooling of that. So going through two steps, we have the nuclei forming, and those are just very, very tiny, just a few atoms start to consolidate together, and then they grow to form crystals into a grain structure. So we start with molten material, all liquid, and a few nuclei. Then those nuclei start to grow out of the liquid molten into these solid crystallites. And finally, the crystals all consolidate together and run into each other, at which point there is no liquid molten left. And each one of these grains is a single crystal that is a different orientation. So the crystals grow until they meet each other. So these polycrystalline materials have boundary. Grain boundary is a misalignment in the atomic directions of the two crystals. So the regions between the crystals are the grain boundaries. And this is an area, we're slicing through it as a two-dimensional image, but if you can imagine this as being a solid crystal, which has an area to it. And the transition from one lattice region to the other is this grain boundary. There is a slight disorientation, this area is slightly disordered. It has a lower density in the grain boundary, which equates to higher mobility, higher diffusivity, and a higher chemical reactivity at that grain boundary. So the grain boundary here, as you can see, it has more spacing. So a high angle boundary is located here. You can see that if you were to draw a line between these planes and these planes, there's the large angle, and drawing a line between these planes and these planes, here you have a much smaller angle. And we'll talk more about diffusivity, mobility, and how that's going to impact it later. Solidification. So grains can be triaxed. That means they're roughly the same size in all directions. And then they can be columnar, which means they're elongated. Here's a micrograph, a cross-section, an ingot that was poured and then solidified. And the boundaries of the casting are here, and so this is a cold wall surface, so the heat is flowing outward. So you're going to have smaller grains near the edges of the casting where the cooling is fastest, and then larger grains towards the center where the cooling is slower. And so what you can do here is add a grain refiner to make smaller and more uniform equiax grains, and that's just like some sort of other material that is used to help the nucleation process and cause the grains to be more consistent throughout. Right. Imperfections in solids. There's no such thing as a perfect crystal. Well, that's really true. So what are these imperfections and why are they important? No such thing as a perfect crystal, just like there's no such thing as a perfect circle. Let's think about what might be very close to a perfect crystal. There are the whiskers, carbon nanotubes, silicon boules when you cast gigantic cylinders that are used to make silicon wafers. These all are perfect within the interior of the material, but they still have boundaries at the edge, and those boundaries are where the imperfections are. So, many of the important properties of materials are due to the presence of imperfections. There are different types of imperfections. We have what we call point defects, which are vacancy atoms, interstitial atoms, substitutes. Talk about those in a bit. Then you have line defects, which we call dislocations. Two or three different types of dislocations. Finally, we have area defects. So these are called grain boundaries. Showed some pictures of grain boundaries in previous slides. So we have 1D point defects, line defects, area defects. So here is a bunch of balls here representative of atoms stacked up. Obviously not close packed plane because of the way they're arranged, but we do have one atom that's missing here, and there's this vacant atom in the structure, and this causes distortion of the planes. It's trying to close off this gap here. If you can imagine that each of these atoms here are connected by a spring, so that's called a vacancy. Then you have self-interstitials, which is an extra atom position between atom sites. Shoved an extra atom in. And that's also causes distortion of the planes. So in the vacancy case, there is a lattice. Lattice is being stretched, so it's tensile here. There's also a shear stress that's associated with this. And again, with shoving an extra atom in here, we have created some extra compressive strains and also some shear strains. So there is an equilibrium concentration of point defects. It is related to temperature. An equation that relates the number of defects to temperature is listed here. So we have N sub V, which is the number of defects, and over N, which is the number of potential defect sites. And each lattice site is a potential vacancy site. Here. And it's related to e to the negative QV over KT. Q is the activation energy. and T is Kelvin. So as the temperature increases, the number of possible defects also increase. And when we get very close to the melting temperature, you can have one lattice site 10,000 that might have an empty lattice 1 in 10,000. That is high, very close to melting temperature. So you do have these imperfections in metals. There are two outcomes if purity B is added to host A. So the gray atoms are host, B atoms are the impurity. Purity has a lower concentration, and gray is higher concentration. So in the case of where the atoms are very close to the same size, then the type of will tend to be called substitutional. We call this substitutional solid solution. This occurs typically with copper and nickel, because those two atoms are very close in size. On the other hand, you might have what we call interstitial solid solution, which occurs when you can get a small enough atom that it might actually fit in the sites between larger atoms. So this is called interstitial solid solution. This might occur with carbon in iron. So look at the the periodic table. You'll see how much smaller carbon is, or how much higher up it is. Periodic table than iron. The other type of solid solution, B and A, plus particles of phase. And this is usually for a larger amount. So when a small amount can remain in solid solution, more and more B that we pump in there, at some point it reaches saturation point, and the B atoms start to out as a second phase. Anonymous like a solution adding sugar, water, salt in the water. So the conditions for having complete solid solubility, or complete a substitutional solid solution, follows the Hume-Roth theory. There's 4 basic rules to operate. First and most important, atomic radiuses between host and purity should be less than 50% different from each other. Number 2, the proximity in the periodic table. So, i.e., this is the similarity in electron activities between the atoms. The more similar they are, higher the chances of having a complete solid solution. Number 3, they must have the same crystal structure in order to have complete solid solubility. They must have the same crystal structure. For example, both must be FCC, they both must be BCC, so on and so forth. Lastly is vacancy. All else being equal, metal will have a higher, a greater tendency to dissolve a metal of higher valency than one of lower valency. Remember, valency is just the number of electrons that the atom uses when it binds with another atom. For example, oxygen electrons that it can give sodium only has one. So oxygen has a higher valency than sodium. All right, let's look at an example of fume Rothery in action. The first case here, which is, would you predict more aluminum or silver to dissolve in zinc? So here's the host here, and here's comparing it with two possibilities, aluminum or silver. So let's go through the rules here and see what we come up with. Atomic radiuses must be less than 15%. Well, here are the atomic radiuses. So if you just take difference here between zinc and aluminum, it's going to be less than 15%. And silver and zinc are also less than 15%. However, the aluminum is a little bit more favorable than the silver in this case. They both are FCC. So we're trying to dissolve it in a HCP. So that's obviously going to be against having complete solid solubility. So moving on to electronegativities. Electronegativities are 1.9 and 1.5. Well, 1.9 is a little higher, so that favoring silver, but they're very close. And finally, last of the rules here is valency. So the valency of aluminum is +3, and silver is only +1. So valency of aluminum really rules in this case with that. And by the way, with the similar electronegativity, you have to compare this electronegativity with this electronegativity. This is the host. So these two are very similar. So that's a good thing. However, at this one compared to this one, they're not so similar. So that favors aluminum. And then what also favors aluminum is the valence. It has a higher valence here. So that is going to favor aluminum over silver. And completes that exercise. So we're going to say that final answer here, aluminum. Aluminum is going to dissolve better in zinc, even though they don't have the same crystal structure. All right, move on to the second one. Okay, I have more zinc or aluminum than copper. So now I'm going to be pairing this one with this one. This is the host. So rule number 1 is similar atomic radiuses. 0.1278 and 0.1431. And but this is also less than 50. Matter of fact, zinc is favored over aluminum. Great. So moving on, similar electronegativities. So if you look at electronegativity values at 1.9, 1.5, 1.9, 1.6. So zinc favored for similar electronegativities. The last of them is valence. So they both have the same valence. So there's no preference when it comes to preference for zinc when it comes to electronegativity, and there's a preference for zinc when it comes to atomic radiuses. So what do you think? Is it zinc or is it aluminum? Look at the most important rule is most important rule is it must have the same crystal structure for pure metals. So this one has FCC, this one has. So aluminum is going to be favored for solid solubility. No way you're going to get any solid solubility, no matter what the concentration of zinc and copper, when zinc is an HCP crystal structure. The correct answer the second time around here is aluminum. Aluminum is going to dissolve more readily in copper. All right, let's look at line defects. Line defects are called dislocations in crystals. This is slit between the crystal planes and result when dislocations move. They produce permanent plastic deformation. Here's an example schematic of a zinc single crystal of zinc, which is HC4 deformation. And after we elongate it in a tensile, as a tensile specimen, we see slip lines, and these are steps in the bar where dislocations so imperfections in solids have linear defects, which we call dislocations. They are one-dimensional defects around which atoms are aligned. So there's two types of linear defects. There's edge dislocation, which has an extra plane of atoms inserted into the crystal structure. And we'll talk about this, what this B is, but the B is perpendicular to the dislocation. And then you have screw dislocations, which are a spiral planar ramp resulting in shear deformation. In this case, the Burgers vector is parallel to it. So the Burgers vector is not the shortest distance to McDonald's. It's the measure of the lattice distortion and direction of lattice distortion. Okay, so let's short video here. That is the extra plane of atoms moving. Watching this again here. Notice how bonds are breaking and then reforming as plane moves through the lattice. kind of like an inchworm moves this dislocation line, moves through the lattice, and it only has to break one plane of atoms. Much easier than having to shear an entire area of atoms all at once. So back to our presentation. Look at a edge dislocation. So the extra plane atoms and we designate the edge of that plane with this upside down T. That designates for an edge dislocation. Now the Burger's vector is magnitude of the change. So if I just draw a circuit around this edge dislocation, and it's arbitrary how many I choose to count by, but I have to do the same number on each circuit. So that's 1, 2. I'm going to choose 2 here, and I'm choosing to go clockwise here. Right-hand rule from thumb into the screen, and 1, 2 down, 1, 2 across, and 1, 2 up. So this here is unconnected plane here of the atoms between here and here is the Burger's vector. So this is the Burger's vector here. All right, so on to screw dislocations. Oh, I'm sorry, back on this one too. Notice here how the Burger's vector is perpendicular to the dislocation line. Dislocation line is running in and out of the page here. So if it's running in and out of the page, then it's perpendicular, which is in plane. On the other hand, here with a screw dislocation, it's purely a shear mechanism. And imagine, like, applying a shear stress to this, pulling it on this side, and we're kind of tearing it, and this dislocation is moving, and you move that way back into this as it opens, as the screw dislocation progresses here. And if you draw the circuit around this one, 1, 2, 1, 2, 1, 2, 1, 2, then the Burger's vector, just that step. Better to draw it to more of them. Get the idea of that, and notice here where the Burger's vector parallel dislocation. This, so this, put it in a slightly different color here. So dislocation line here and Burger's vector here, so these are parallel. So you can have a mixture of edge and screw, and this is called a mixed dislocation. And in this case, dislocation line curves that makes a 90-degree change direction here as it transitions from a through dislocation here to a edge dislocation here. So all this area fixed dislocation. All right, so dislocations are visible by an electron micrograph. This is using something called a TEM, or transmission electron microscope. It's able to resolve highest resolution possible. It can resolve individual atoms. And the picture on the left here, all these little whiskers here are dislocation lines. So there's never a perfect, dislocation. They're always mixed some sort of way. And the cool thing is somebody made a video of a dislocation, and let's watch that. So here you can see worms kind of cruising through the crystal and spreading out. Sometimes they get hung up, or pinned at certain levels. And later on, we're going to learn how important dislocations are to determining strengthening, because it's the hindrance or the pinning of dislocation that allows the material to not deform as much. Remember, dislocation movement is just deformation of material. More on that later. Dislocations and crystal structures. So dislocations prefer closed packed planes and closed packed directions. Remember earlier, closed packed are the plane atoms are closest together, and here is closed packed plane. Atoms are very close together here, and so this is another closed packed plane of atoms with stacked close as possible on top of that. And so they prefer to move along these closed packed planes. This is the movement we're talking about. And it prefers to move where amount of stretching between the atoms, or they can attach. And the other neat thing about this is that the number of bonds that break is much less when it's out of plane, packed plane. If it had to move in plane, there are 6 atoms here that this atom is attached to, whereas out of plane, only 3 bonds. So only 3 bonds have to break. Slips between the closed packed planes. That's much less than having a slip in some other plane, 0 or the 100 plane. Back to So the comparison among crystal structures. FCC has many backplane directions. HCP, there's only one plane, 3 directions, has no closed pack planes. So if we do a tensile test for 2 types of materials, say aluminum, which is FCC, it has many closed pack planes. It's going to have more deformation and higher ductility than a magnesium sample, which tends to be very brittle. HCP, it only has 3 directions that are available for SLED. In summary, we talked about point defects, line defects, and area defects, and how they exist in solids. The number and type of defects can be varied and controlled, e.g. temperature controls the vapor concentration. The defects affect the material properties. For example, grain boundary controls crystal split. And defects may be desirable or undesirable. Dislocations may be good or bad. It just depends on whether plastic deformation is desirable or not. That concludes Chapter 4.